This is what a real atom is constructed like. It's not a big ball of positive and a couple of little negatives floating around. No, it's made of dipoles. But when you get them in a cluster like this, the black part of the dipole goes to the center, surrounded by the energetic particles that all want to get to it. That's how electricity works. These electrical particles, the electrons, travel into the ground, which is the black. Ground because it's mass. It's ground. This has no mass to it. This is ground. All right? When you make an atomic bomb, you make it so big with the energetic particles surrounding this black mass that it's just totally unstable. It wants to completely explode apart all by itself. It's fissionable. You get near it with a radio, oh boy. Okay, to make you understand how dipole electrons work, we're going to blow up a house. This was called the Teapot Apple II house atomic bomb effects. They got a truck here and all this stuff. They got a building, a little town basically, to see what happens when the explosion goes off. How does it react? And it's in extremely slow motion. And I'm going to show you now. Dipole electron flood theory is my theory of how atoms are constructed, and it's not like the Standard Model. Standard Model has one big, huge black core of solid, positive protons, and then around it there's a couple of little floating electrons. That's not how it is. It's dipoles. It's one for one. And when you build an atomic bomb, you make huge amounts of dark matter in the center, the black particles, and so many that they just want to explode and fall apart, and so many electrons come around them and crush around them. So when they explode an atomic bomb, they push it in and it pops back out, and the white comes out first and the black follows. So it's pushed in and then comes out. The black pushes the white. I'm going to show you that in an atomic bomb. That's exactly what happens. Okay, my friends, this gets very deep, but I am going to show all the particle physics that people are going to have to... Okay, my friends, this is a strange motion keeps appearing everywhere in high energy collisions. And these are the fields bouncing against other fields, basically is all it is. They call them Levi walks, wherever that name came from. Particles in high energy nuclear collisions, and that's what I have in our work is nuclear, and it's subnuclear. Move in a way that follows a pattern known as Levi walks. They're just field bounces. That's all it is. They want to call these Levi walks, that's fine. All of these are nothing more than Higgs fields. And they're coming back together after the separation of the white from the black, and the white now is recombining with the black right here, turning into fields. As they come back together, that's fusion. Now, this Levi walk thing, I have no idea what they're talking about. These are Higgs fields coming out of the Venturi at us, recombining with the black particle, the white, and turning into Higgs fields. That right there, I believe, is antimatter. That one there, I think, is spinning backwards, which is the only one I've seen. Now, this is one of the first ones I saw of just space. These are what I think they're talking about, these Levi walks. They're just concussive magnetic fields that surround dipoles. Everything is a dipole, and surrounding that dipole is magnetic fields. And I'm working with a whole bunch of people now. Look at this thing. I believe that's Saturn, and that's dipole fields, and it's a strange situation. It's a little bit stranger than the average. And these are some new techniques that some people are using and sending them to me because they're not getting anywhere with mainstream science. They don't want to know about this stuff. Anybody that doesn't do anything that they can figure out some way of making money on, in my opinion, that's what happens. Now, this is the atmosphere surrounding the Earth. All right, and this is something severe is going on there. This is California. Now, the atmosphere surrounding the Earth goes out to a certain distance and basically stops. But that part scrubs with the Earth as it spins, because the Earth is a globe. It spins, it travels through space, and when it does, it scrubs on this atmospheric layer right here with the atmosphere of space, which is not a vacuum. It's not a vacuum. It's completely saturated with particles, which I showed you. When we scrub through that, this gets up to thousands of degrees. Thousands. By the time it gets down to the Earth, it's only like 100 or so in that area. But between here and Earth, it gets down to minus 100 and something degrees. It's just absolutely amazing. Hot, cold, and then hot again. And then Earth absorbs that heat. And the Earth now has absorbed more than it's supposed to. And the enzymes that are in the Earth are now turning on to do decomposition. And when they do, they create greenhouse gases, methanes. They're all over the place. And the atmosphere is swelling, and these gases are not good. The sun has the same situation. It's 10,000 degrees on the surface approximately. Out here at the corona, where its atmosphere is scrubbing, it's millions. They have no explanation for this at all. From here to there, how did they get from 10,000 to a million? Who added the temperature? The temperature is because it's scrubbing here. And the same with ours. How did it get from 100 to thousands? It's a scrub. Virtually no question about it. Now, if you know how to really think and observe, you can see what's going on here. The first thing you can see is this polarity. You see this shooting straight down, that's shooting straight up. All right, that's the polarity of the sun. The sun is behind here. The moon is obscuring. So this is a solar eclipse. We're on top of the disk of the sun, so we can see all the particles coming out, but we're not being blinded. You see these three red spots? Those three red spots are because there's more concussion there, and they're creating magnetic fields surrounding them, and there's more concussion there. It's hotter. The only reason that would happen is if the sun was spinning in this direction and moving that way. So these would be the hot spots. And this would be the trailing off, which it is. You don't see this same effect on this side. So the sun, in my opinion, is moving that direction and spinning in this direction, which gives us these magnetic fields and gives us this trailing off effect. And all of this is particles that have to go somewhere. Once they reach a certain distance, they're gone. And here's what I'm showing here is a little drawing that I did. Coming out of the sun, that's the surface. We got the corona, which I just drew it out of here. Now, coming out of there, you see this? These little spinning particles? They're spinning through space. They're just particles. You don't see them hardly. There's a little glow out there, but that's about it. And then when they hit our atmosphere here is when they collide with the atoms that are here. And they're being drawn to the Earth because the Earth is primarily dark matter. Anything that has substance to it is dark matter. It's primarily dark matter. The light part of light, the white part does not. You could just do this, but not the dark part. The dark part, when it congeals into a mass, which is the mass basically like the Earth, You can walk on it. It's got substance. And that's, as Don Lincoln says in Fermilab, that's exactly what it is. The black has the mass, the white has the energy. Normally they're together. So normally this would be black and white all balled up together in different quantities here and there, called molecules, atoms, whatever you want to call them, mountains, trees. But they're solid material because you have the black added to the white. And I believe there's more black inside the Earth than there is white, because the white is attracted to the Earth desperately. Lightning, electricity, right to ground. This is ground. Now, this just shows you the atmosphere. You know, this is just a little drawing, but the atmosphere in space is saturated with particles, just like it is here on Earth. Virtually no difference, except they're a little more separated out. But they're out there. I mean, there's particles everywhere. These are, you know, I'm working with a guy now who has a Newtonian telescope with some kind of fancy stuff going on. I don't know what he's got, but he's got some serious looking stuff. Now, if you look at this carefully enough, you can see that there's not exact dipoles, but there's dipole densities. Like, you see how bright that is right there? And you see how dark that is right there? They're pretty close. Now you see how bright this is and how dark this is. And the rest of them, they're sort of evened out. But you still see them. You see it dark and white, dark and white. Everything seems to be a dipole. But then you can get to places which are pretty even. Look, you don't have a whole lot of dipoles here. I don't know what's going on. You got this little thing, the thing. Some of this stuff is just stunning. It looks like little waves. Like this thing is doing something. I don't know. But Mason is doing this, and it's amazing stuff. You know, I've been looking over Mason's stuff here, and at first I was wondering whether these dipoles were here close to Earth, and he's just taken he's got a Newtonian telescope, whether he's looking through this and seeing these little dipoles and then going out and seeing that way out in space. So I've been looking at it. Now, I think that's not the case. I think he is looking at a dipole here. Look at this thing carefully. Think about this logically. You see how bright that is and less bright that is? Basically a dipole. You see how dark this is and how bright this is? Basically a dipole. You see these particles here? How dark they are basically compared to how bright these are. These are just dim compared to these, in my mind. So I would say this whole picture is out here surrounding whatever that planet is. I don't know what it is. It could be a moon, could be a planet. I really don't know. He just sent me a whole batch of pictures just to take a look at, see what I thought. And this is what I think is energy is here, and less energy. Well, you know what I mean. The black, it's a dipole. This is the dipole side black, and this is the dipole side white. That's all I can take from that shot. Other than that, but I would say these are somewhere out in space and not here on Earth, these little particles. That's my take right at this moment. Let me just go one step further. You see how lit up the side of these dipoles is? This side. And the other side is dark, but it's not real dark. This side, the dark, is on this side. And the white hangs off that side. I would say this has to be affected by this side of the dipole, and these are affected by this side of the dipole. And if we're seeing that dipole way out in space, these particles have to be out there with it. If they're being affected by it, they have to be out there with it. Otherwise, it's not going to affect it here down on Earth, I wouldn't think. And you can clearly see it's a dipole. Okay, I just got something from Marilyn B. We've seen these two heavy particles smashing and all kinds of bits going. Now look at this. They just came out with this. This is the same thing. They're coming together, these two big boom, and out goes a bunch of stuff. That's how they create this super collider. Out goes these glowy particles. And they have the dark and the white, and then they change as they go forward. Let's see if we can see how they change. What are they seeing? They're seeing these huge balls come crash together, and then they're seeing a whole batch of debris like this. And then they're seeing it sort of flatten out in these particles, and then whatever this is about. And then they see the black and white particles, and then they see only the white showers. Can we see this in our experiments? Because we did the same thing, only we came through a Venturi. Instead of hitting and letting it bounce back, we went through the Venturi, created the same thing. Basically the same thing, only we didn't have to deal with this. We just had that. All right, so here they are. Atom Central. It's a Teapot Apple II Q House atomic bomb effects. Now, they're going to get the truck out of here and all that stuff. They've got a hardened enclosure looking at this, so it's not going to get affected by the atomic bomb. And it's going to watch what happens as the radiation comes forward. All right, now I got to run it real slow, and I'll explain to you what goes on here. The first thing that's going to happen is everything is, it's going to start off totally dark. And when it flashes, I'll stop. Boom. There is the atomic bomb just went off. What I want you to look at is up here and the roof and anything that's combustible. And when I say combustible, metal things like metal tanks and so forth, they're not combustible. They won't burn, but watch what does burn. All right, I'm stopping it again. Watch the poles, watch the wires. Of course, that's not going to burn because it's metal. The facade of the house, the roof of the house. Look at this. Now, this is the preceding part, which is the white. Remember I showed you, you got black pushing the white? This is the white part right here is being burnt up, everything that is passing by. But you're not seeing it push. It's not pushing. What the hell is going on? It's just the white part, which has no mass that I can help find. It just burns because its energetic field is now entangled with the other energetic field, and they're pushing back, and it's got something to do with oxygen and combustion of these fields. The fields pushing together do something in the oxygen realm as it appears. And I'm not sure what exactly, but that's what's happening is field to field. Now I'm going to continue on here. Watch. It's just nothing. Nothing other than just burning. Now all of a sudden the black will come and hit it. Boom. You see that? That's exactly what I showed you in this here. It comes through the Venturi like a nuclear explosion. Out the white comes first and the black follows it, pushing it. All right. Out here you see the width of these waves? They call these Whistler waves. And that's exactly what they have in an atomic bomb. They have a Whistler wave, and if you're way out here, you're going to hear, and then out comes this, and boom, then you get your pop. But way out here, almost instantly when that goes off, the magnetic fields push, and you get Whistler waves. And I actually have that. Well, I probably should show it to you. It just goes, and that's what you hear ahead of the atomic explosion. All right, I'm going to just let this play because this I did a couple years ago. And this is the atomic bomb blast. And the first thing you're going to hear is, brrr. Now I'm going to turn it up pretty loud here so you can't miss it. Here goes. Before we hear the concussion, listen to this. Did you hear that? You didn't see any nuclear blast yet. You can see it. But now it's coming at us. You see this? This is the dark particles coming at us. That wave coming across the desert. So we have not heard anything other than that. Blah, blah, blah. Now we're going to hear the blast. That's the blast. All right. You understand what we first heard? Let's do it one more time. They're getting ready to set the bomb off. Here goes. Did you hear that? That's the Whistler wave. As a matter of fact, I'm going to re-up this, and you can see this whole thing because it was very detailed. I mean, I showed all the particles. I showed them accelerating. I'm showing the same thing that I'm talking about for a plasma engine. This can be done in space. This is just working with light. And these are the particles that would be spewed out the back. Now the Russians are trying to work with an ionization accelerator. So they're working with ions, which are bigger particles. And it may work better. I don't know. This may work fine. When you're in space, you're only pushing against what you're pushing against. So they may have, it's hard to say. I think fields are going to push better in space than actual particles. Because the particles themselves, the ions themselves, I don't think are going to have the energy that the fields do. And this is nothing but fields. And they're going into nothing primarily but fields. Everything has a field around it. But the black particles are not going to be as reactive. I don't know. Something we have to take into account. But I know these fields take up huge amounts of space. And everything has a field around it. And field to field creates this energy, and it makes things go very, very fast. Okay, this is from a channel called Sci Explained. And it's the Russians unveil plasma engine for month-long Mars trip. Well, they're creating plasma here, and then it's got a charge to it. So they're accelerating it or doing something. I'm not sure what they're doing with it, but they're calling it magnetic accretor, magnetic field, and they're sending it down this tube. And it's just like squirting out through a balloon, and that's how they show it. Now listen to what they have to say here.
Electric fields. These engines do not burn fuel and expel gases under pressure like traditional chemical rockets. Instead, they generate thrust using electromagnetic forces. It sounds complex, but we can observe a similar effect in everyday life. If you inflate a balloon, hold its opening, and then release it, the escaping air rapidly pushes the balloon forward. This is Newton's third law, the action-reaction principle.
Basically, that's what we're doing with the dipole electron flood device. We're at the end of a rocket, let's say is right here, and out of that is squirting the laser. It explodes here and forces like crazy, as we've seen. And I'll show you again so you understand. This is basically the same thing, but the laser is built right in here. All right, this is the whole rocket ship. The laser's built in here, and that's where the Venturi is. So it's going to force this to go very, very fast as that goes very fast out. And because we're using magnetic fields, we're using the white part of the particle, it should really push fast because there's going to be fields everywhere. There's nothing but fields out there. So field to field gives you the Casimir effect, and that's where you're going to get some acceleration. I don't know if this is going to work as good as what we're showing. Okay, this is about this new thing they're calling the Levi walk, a motion found in all kinds of fields in science. It's just a collision of the zone of magnetic influence, basically. And they say particles in high-energy nuclear collisions moving away follows a pattern known as this Levi walk. It says their findings challenge traditional assumptions and connect nuclear physics to broader scientific disciplines. Everything is made out of energy. You bounce things together. It's broader, yes, it's everything there is made of energy pushing other energy. All right, here's what happens with pushing against other fields. You get field to field, which is nothing more than everything's covered with a field. So this plate has a field, this plate has a field. They come together, this pushes apart both directions because it's field to field. Field to field gives you acceleration and push. Okay, my friends, this is exciting. The Russians announced that they have a plasma engine now that they say they're going to be able to get to Mars in 30 days. And I'm just going to play this. It's from a channel called Sci Explained. Now here it goes.
Gases. Inside the engine, this gas is exposed to a strong electric field, which ionizes it by stripping electrons from its atoms, leaving behind positively charged ions. Now we have ionized gas, or in other words, plasma. This is where the magnetic fields inside the engine come into play. These fields accelerate the positively charged ions in a specific direction and eject them at high speed from the rocket's exhaust. The principle is actually very similar to how traditional rockets work. Chemical rockets burn fuel to create high-pressure gas and expel it, while plasma engines accelerate and expel ionized gas.
Okay, that's enough. They're talking about ionized gas. They're talking about big atoms, and then they ionize them, which means they strip electrons from them. And then they become positively charged, but they're positively charged just means they have more dark matter than the white matter. All right, this is really interesting because an ionized gas, they call it plasma, is the state of matter where the atoms, with all their little particles, get stripped away of their electrons, creating a mix of positively charged ions, the atoms that have been ripped for the negative parts, so they're positively charged, and free electrons in this mix of plasma. So don't forget now, we got the black particles, and then we got the white plasma, which it has no mass. The black has the mass, and the black attracts the white. All right, the black is the ground. It attracts the white, which is just nothing more than electricity, lightning, static. It's the white seeking the black. Okay, my friends, there's only one way to do this, and this is to start right from the beginning. Dipole electron flood theory replaces the standard model. And it works flawlessly. And I have experiments to prove my claims. So let's start right from the beginning. When years and years ago, I was deep into everything as far as energy and temperature and light and heat and chemistry, everything. Every science I could get into, I was in as deep as you could get into it. Because it was really, the beginning of quantum was at that time, 1970, in that area, is when I really got deep into it, because I was in the Army, Nike Hercules missiles, and, it took an interest in it, and in my whole life, that's what I did, into electronics primarily, troubleshooting electronics. And I learned a lot about it, how energy works. And electricity, there's so much to it and so little to it, it's hard to believe. It's so simple, but it does so much, and it becomes very complex when you start to try to manipulate these particles. But you can also do it easily. It's one of those things that it's hard to explain how simple it is, because it's always been made to sound so complicated. Let me show you how simple this is. And it is simple. I mean, it is simple as simple can get. Now, like I say, after I got out of the Army, I went into to study everything there was to do with quantum and all of that stuff. And I came up with a theory at that time, which was that the transfer of energy is from light into atomic vapor. And I'm going to show you the atomic vapor. It's right here. And that atomic vapor congeals together just like water vapor. Moisture in the air comes together and makes water molecules. Well, the same thing with this. Light comes together to make atoms. And light can be extracted from an atom as a dipole, and these are them right there. And they've done this by smashing atoms right here at the huge particle colliders. They smash atoms, and they can see these are the two tiniest particles. They call that a Dirac neutrino when they're stuck together, and these are them right here. This is from our experiments. This is from Fermilab's experiments and CERN. But they don't really see them together often because they're just so much of a splatter. We're working with light, which we started with a very, very tiny particle. They're starting with huge masses of particles, hitting them together, and this, all kinds of stuff goes flying. We're started with this, which is just this right here. It's the tiniest particles that exist. And then it broke apart at the Venturi, the white left the black, which is, in my mind, it's fission. The black separates from the white, and it came back together here as fusion. And this is in the subatomic realm, so it's nuclear. So that's nuclear fission and fusion right there. And this is dipole electron flood theory. And I'm telling you right now, to get some credibility, I did this my entire life. But this goes back to the earliest days. And I mean, this book is saturated with nonsense. Because it was. I checked everybody's theories, and there was nothing that worked. Not a single thing worked. Not a single thing worked. Pauli principles and all this kind of stuff. Right up here, some Rutherford's atom was wrong. Rutherford's atom was wrong. Einstein was wrong. You can accelerate light. Light slows down, not just in a medium, just light slows down just naturally. Well, if you could have a perfect vacuum, but there is no perfect vacuum. This is what space is like. This is what space is like. I'm working with people that are so advanced, they're way ahead of NASA and all the rest of them. Look at this. This is what space is like. This is Mason. These were the Russians went out there and did a charged particle of dust into a vacuum chamber, and they came up with this. They freaked out. During the experiment, we contacted the Earth guys who couldn't believe it either. As I recall, one of the guys from Max Planck University, or I believe it was Max Planck, locked himself in his office for 3 weeks. They couldn't figure this out. Not only that, it created a double helix in space, but only under cryogenic, which is cold as cold can be. It did this. This is from these Russian, because I'm going to do a whole nother video. It's going to be quite long because I've learned a lot since this. This was 2015. I think it was 2015. And I followed it very closely, and I understood a lot about it because of that black hole. And there's things that they didn't understand because the outside of the enclosure They have a vacuum in here, but it doesn't matter because the surface is going to always be coated with the white particles, and the white particles push other white particles away. So they end up collecting in the center, and you can see it's a little flat because they're in low Earth orbit, so there's still pull to Earth by gravity. Now at Earth, this would just be flat as a pancake. All the white particles would be right against the Earth because the Earth is ground. Out here, there is no ground. So they have to come out with whatever they can do, and they push their own ground right into the center, which is dark matter. That's what it is, dark matter. And they didn't realize it, and they still don't realize it, and they had found it many years ago, as we did in the light experiments. This is dark matter. It really is dark matter. There's their dark matter. It has all the mass and a glowy edge around it because it's trying to attract these. These want to always be attached to that. And here they are attached back to back as a photon. We separated them at the Venturi here, which is fission. They came back together as fusion. And this is the strong nuclear force. This is what they call a gluon now. To me, that's a dipole electron. And on its own, it's heat. Back to back with another one, it's light. Light bounces. Heat is attracted because it wants to bond with something, basically. It's not really bonding. It's sort of adding in to something that's cold, and it wants more energy. It wants more particles to become as warm as everything else in that area. So it'll accept some just floating around electrons. And you can get the white particles stuck on you as static. And they also create lightning, electricity. It's just the white particles. So there's a little bit of a variety here. And we can accelerate them. Light is a particle, as I showed you, right there, that's light, that's the particle. And as it goes through the air, it creates a wave because there's a field around it. When the field crushes at the Venturi, you get this acceleration right here. And of course, it fizzes and fuses. Well, I'm just going to go from the start of when I started to understand this years and years ago, but I had no evidence. This is from the start of when we started to have evidence. Rod Warren did this just by accident. And this was the wave that he could see using CMOS. And I'll explain that. It's complementary metal oxide silicates, semiconductors. And they pick up on radiation, frequencies of radiation, where they're just phenomenal at doing that. These are the camera phones. These are the phones that are in the cameras. And this goes back to 2012. So he started showing these, and I started working with him. And I realized that he was displaying what light is. All right? And these were the particles. And the particles push forward, creating this wave. So we have particle-wave duality. All right, and you can also see that the leading part of the particle, these are the same particles, and this is another thing that CMOS can do. It can amplify and show the very, very excellent details and the frequencies, because these are in colors too. You see all these colors? I'll show you in a minute. This one's glowing much more than that, because it's leading and hitting this way, causing much more interference in front of it, pushing particle to particle, makes things glow. All right? And so this one is glowing, and in a minute, a bazillionth of a second, it'll go blip, and that one will go in the front and start to charge up. So you have downspin, and then when that one goes forward and this one's over here, it's charging up, that's upspin. And that's all you have, because it's always going to be parallel to the Earth. All right, we did tumble them by putting them through the Venturi at the same time. That's the only time I've ever seen them do anything other than be straight up and down to the Earth. Plus, light doesn't flap like a wave. It spins like this. That's what light does. It's a spinner. And I could prove all the things I'm saying. I'm not making any guesses here whatsoever. None. Zero. Okay, that makes it pretty obvious light is spinning. And when it spins through this double slit experiment, it's not flapping like a wave and doing this and that. It's just spinning. Some goes that way, some goes this way. When they come out the other side of the venturi, which is the slit is a venturi too, they create these patterns which are repulsion patterns. They say, you stay away from me, I'll stay away from you. Boom, 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 boom. And that's what creates elegant, elegant patterns. And here you can see every detail. On a normal double slit experiments, you just see basically interference, the big globs in the back. We see them actually turn exactly identical to a drill bit, spinning this direction. It's concussing here and then dipping down and concussing over here and then dipping down. It's just like a drill bit. And most of it's going through the center, which is the first point of impact. All right, this is something you should also know. I did all the experiments about heat. Heat is nothing more than extra electrons. The more electrons you put in, the more heat you get. So these were the three things I was checking here. And the heat of neutralization, heat of solution, heat of reaction. And these were all of the different tests I did and so forth. And what happened and what the changes were and so forth. And I came out with a conclusion that power it's always electricity. You see, I came from heat, all about heat, into electricity. Electric power. All power is electric. Everything there is that has energy is field to field. That's what electricity is. And then you can calculate power in watts and all that business. But this goes way, way, way back. Okay, this is actually backwards. The Dirac neutrino is correct. However, this is the matter. That's the dark matter, and that is the mass. That's the thing that knocks the house over in an atomic bomb. This is nothing but energy. It makes a house just burn up and combust. They're always locked together tight, unless you do the super collider or you do what we did, which put it through the venturi, and then they separate. And they can separate in other ways too, because you can collect static electricity on yourself, and that's all you're going to have is this glowy part, which has no matter. It has no mass to it, that I can find. Therefore, it has no weight. Otherwise, it would have pushed the house, as I showed, I think, already, the house being pushed during an atomic bomb. And the only thing that pushes it is the black part, and the black part is the part that catches up to the white part. All right, the black part is in the center. When it explodes, all the white parts go out first, and the house just burns up like this, like vapor. And then all of a sudden the black follows, and boom, there goes the house. That's what an atomic bomb does, and that's what light does when it leaves the black. And it doesn't leave the black ever until you do either like the atomic bomb or what we did with the venturi. You know, that's not right. What I just said is not correct, because we do get extra electrons floating from here to there. You call them ions, whatever you want to call them, but the electrons can float and collect extra and want to get away from the surrounding that they're, boy, this is tough to explain, but what you're going to have is extra electrons can float here and there, and that's electricity. That's what causes lightning. It causes static from you touch a water pipe, snap, if you have extra particles on you because of static and so forth. Electricity is nothing but the white particles moving to find ground, which is the black. I think I've explained this. This gets a little tricky, and I need to do some interviews with some electronic engineers and so forth to talk about the flow of electricity, grounding, and what I'm showing here in all my light experiments. This is real. And you know, I know I've said this a whole batch of times. I didn't go there, but I actually took a course at the University of Geneva and talked to them about seeing the dipole electrons using light. And at first they dismissed it because they said it would destroy the CMOS. And I said, we're using light, so we're using the smallest particles, which CMOS is designed to pick up. It's picking them up on steroids, no question. That is really, really hitting that CMOS, absolutely. Power is absolutely amazing. However, it's designed for that. It's not designed to be hit by particles like this. We're hitting it with particles like this. It doesn't destroy it. And they finally did agree. And shortly thereafter, whether it had any reason to do with me, I don't know, they upgraded CERN to use CMOS for detection. All right, pay attention, because we're going to need new physicists. This is just not right. They just don't understand what's going on. They're taking these huge particles, protons and neutrons, bam, they hit together and they just splash. They don't realize they just took two of these and hit them head on and had chunks flying everywhere. X means could be anything. All of these other particles we have found, photons, the red, the blue, the green, we found all of those in energy states. X just means a big thing. We're never going to find any of those because we started with light. We started with that particle. Now they're seeing this one not energetic photon. This one is an energetic photon. Some of these are energetic particles, and some of them are the same particles that are not energetic. It depends on where they see them and how long they've been decaying for. They see crazy looking things that really don't exist. They're particles that shouldn't be particles. And the X is just like a chunk of this, and it does not want to stay like that. It will have to add more or decay some more and give up a bunch of its particles, because it's just not going to be stable at even the tiniest bit. It's got to just, that's why you hear radioactivity, because this thing's just spitting out extra particles or taking on extra particles, whatever. Most likely spitting them out. But anyway, this is what they're doing. That's just not the way to do it. It's just not the way to do it. Okay, just so you know, this is the particles that they had in the article from Fermilab, and these are the same ones right here. They're virtually identical, no difference. So the black with the glowy edge around it, the white can get bigger and smaller, has no mass, and this has all the mass. And that is exactly what Don Lincoln wrote here in 2013, and I contacted him about this. I said, we found your particles, and it didn't go too well. But that is his article. Actually, this is copied right from his paper, which is right there. All right, now here's also talking about empty space isn't empty. How could they expect the light not to slow down if empty space isn't empty? And it isn't empty, he's right. And back again, I sent them information about that as well. You want to see what space is like? Does that look empty to you? And it's exactly what he says. It looks like the head of a root beer, all bubbling and crazy like that. He actually points to the head of a root beer. You see it? Quantum foam, they call it. Empty space isn't empty. Well, you know, they make these statements and then can't talk about them. Okay, my friends, it's a new day in electronics. It's a new day in physics. And a dipole electron flood theory has to be understood and examined and thought about and discussed according to the evidence that exists, that it makes it hard to dismiss it. So we're going to talk about this. Now listen to me right now. This is important. If you want to become something, You have to understand the basics of life and physics. You have to understand matter. You have to understand how to think and how to resolve issues that come up to say, ooh, that can't be right. How could this be? How could that be? If you just listen to what you're told and you think you're going to be smart because of that, you're in trouble. You're in deep trouble. Because physics is wrong, and there's a lot of other things that have been wrong and dismissed because they go against the mainstream peer review. And once you get into that peer review, they won't review you if you have evidence that supports your side against them. And it's a group gang mentality. They keep you out because you exceed what they have. And this is it right here. And I'm going to show you right now dipole electron flood theory. And it changes everything. And the Russians just released a new engine that they claim they can get to Mars in a month using a similar technology as this. But I don't think it's as sophisticated as this and as simple as this. This is as simple as it gets. Only I think this is much more usable and much more powerful than what the Russians are proposing. They're proposing ionization. I'm proposing pure, raw dipole electron power. And I'll show you the difference. Now, this is the same style Venturi, only it's tuned in such a way that it lets black and white through. Only the white, it precedes the black, so it's pushing. The black is actual matter, and this I can prove. All right, I'm going to give you a little demonstration here. This is that Venturi. This black is actually matter. That's the black part. The white is just not matter, but it's energy. I'm going to show you a nuclear explosion, which is exactly what we do here. This is literally a nuclear explosion, subatomic. And the black and the white separates. And the white comes out ahead of the black, just like happens in a nuclear explosion. All right, my next video is going to be on plasma physics, the whole shooting match about light becoming plasma and how it can be used. Now listen to what they have to say. This is Psi explained again here. Now here we go.
Pressure gas and expel it, while plasma engines accelerate and expel ionized gas. But there's a critical difference. Plasma engines do not generate thrust by burning fuel. Instead, they use electromagnetic forces. According to Newton's third law, when ions are ejected from the engine's exhaust, the rocket gains an opposite thrust and moves forward. So it's not just about expelling gas, but about accelerating ionized gas at high speed in a controlled manner. To achieve this, instead of a simple chemical reaction, plasma engines use much more advanced electromagnetic acceleration systems. Since we have come this far, let's explain why plasma engines are better than chemical fuel engines. To put it simply, accelerating ionized gas with a magnetic effect always produces more thrust than expelling burned gas.
All right, they're talking about ionized particles. We don't need to do that. We can go directly to 100% plasma without going through the particle phase. You don't need the particles. We need the plasma. We need the fields. And we can go right to the field using the Venturi effect if it's tuned correctly. It's got to be designed right, and it will separate completely the fields from the mass. And we want the fields to accelerate, because a field against a field will push you faster. If we went field with the dark particles against, I don't think you'd have as much push as field to field. Field to field gives you the Kashmir effect, and that's pushing back in both directions. You'd be pushing from this way and pushing this way. You'd be really rocket ship out faster and faster and faster, I would think. We got to look through it, but I think that's the real payoff with plasma. If you can get it to completely separate from a dark particle. I think it will give you more push. Now don't forget, white pushes the white. Those two push apart. The white pushes apart from the white. The black attracts the white. So if you're shooting through with black and white, the black is going to attract white over here or whatever. We want just the white to push the other white, and then we're going to get some acceleration, I would think. All right, this is the Russians again. This is from July this year, 2025. Now, it says it would take a year to get to Mars using conventional things right now. However, they want to use this plasma engine, and they're saying it could reach periodic impulses of 300 kilowatts. Now, the engines enable spacecraft to accelerate in space velocities beyond the capability of chemical engines, make fuel consumption more efficient by reducing the need for fuel by 10 times. What I'm talking about, I don't think you need any fuel at all. I think you would make your own energy, and you could just recycle it back in and just keep shooting it out. I think we could do that right now and generate free energy using some of this stuff right here. Harvest that energy right there. When it comes to the Venturi, the white is completely separated from the black, and that's what energy is the white. That's what electricity is. That's what energy is. Before it was together, now it's separated, and we have the black separated from the white. We just want to harvest the white. And I don't think it's going to be all that hard to do. I've been trying to push this for 10 years now. I can't get anybody to look into it, but I think maybe the Russians did, because they're basically doing the same thing. They're talking about this. You're seeing the end particle flare after this glob of stuff goes back this way and starts to disintegrate. It looks like, I don't know what they're talking about, all this stuff. But coming through is all the particles coming back this way. They're bouncing back off of this nuclear explosion. They came bang, both sides, and then this hit and came flying back. All right, so at this point, it's really energetic and glowy. And then it starts to settle down a little bit. And the black filters out. The black stays back. And the white ends up splaying out in the end, creating this free streaming electrons. That's what I'm seeing. That's what we did. Only we didn't have to start with all this big stuff. We started basically here. You know, pretty much. All right, CERN is upgrading and has upgraded to put in CMOS, basically the same thing we did, to see these high-speed particles. We can actually see the plasma. Now, they claim they can't see it, and I think they can, but they say they can't. Now, it says, while CMOS detectors themselves do not see plasma directly, I think they do. They are exceptionally well suited to detect the subatomic particles, yes, that emerge from the QGP's rapid expansion and cooling. It's the explosion of these particles. Precision tracking these particles, scientists can reconstruct the properties of the short-lived QGP, quark gluon plasma. Quark gluon is just a black and a white particle. Gluons are the black and a white particle. They can reconstruct the properties. We've already done that, and we've done that for quite some time. Now, like I say, I will probably go into this deep again. Sooner or later, it's going to have to be understood, and we did do this. We understood the particles, the photons, the muon, electron, neutrino. Back to back is a photon. A single set of these is a dipole electron, which is nothing more than heat, basically. It has weight. Electricity has no weight. Electricity has no weight. You take a battery that weighs 40 pounds, and it's totally empty. Well, let's take a car. Let's take a Tesla. Let's say the Tesla weighs 4,000 pounds and it has no charge in it whatsoever. You fill that car up with electricity, it still weighs 4,000 pounds. You drive all day long, drive around till there's no energy left, it's just done, still weighs 4,000 pounds. You fill it back up, still weighs 4,000 pounds. The white part that you're pushing in there has no weight. And I showed that, I believe I showed this time in the nuclear explosion. It just has no weight, it just has energy. See, I'm not just making it up. Electric car does not gain a measurable amount of weight when charging because no physical substance is being added to the car. You're adding electrons. Charging stores energy through chemical reactions. Well, yes, I more or less can go along with that. And while the stored energy itself does not have a mass equivalent according to E equals mc squared, the resulting weight increase is so minuscule. So they are saying there's some 4 micrograms for a typical 100,000 watt hour battery. It's completely undetectable. You can't, they say 4 micrograms. Well, I would always think there has to be something that's supporting this magnetic field that's just a big ball of energy. There has to be something there. And they're saying 4 micrograms. That's 4 thousandths of a gram when you're talking a typical 100 kilowatt hour battery. That's probably, I don't know how big that is, but all right, the 100 kilowatt hour battery pack weighs at least 900 pounds up to 2,000, depending upon what it's made out of. But it gives you that amount of energy. So you got 4 micrograms, which is 4 thousandths of 1 gram. 4 thousandths, it's like a couple of grains of salt for this big of a battery. I mean, it's imperceptible. There's no way you really could measure this. And I did see a guy measure it, to try to measure it, filled his car up, drove around all day, filled it back up again, never changed even a tiniest little bit. And he had it on set up on weights and scales, and it just doesn't change. And they say 4 thousandth of a gram is the change. You want to see something exceptionally cool? This is when the stuff hits and you get one blast and you see this. Well, we were using a pulsed red laser, and look at this. This is each pulse. That's the back end of the pulse. You see here? That's the pulse going through the venturi and splaying out on the other side of the venturi. And that was the pulse that was ahead of it. They're a certain distance apart. And this is a measuring pulsed red laser. And I believe, I'm not certain, but I do believe, this is the leading edge of this pulse. And this is the trailing edge right back here. You can still see the corpuscular nature of the particles. Each one of these is basically a particle. And they had to force themselves in through the venturi, creating energy. And when they came out the other side, they do spin, and they spin to the right. It's right-hand rule. If it's going that way, it spins this way. And you can see it. This is the last pulse that was just before this one. The distance is that much of a distance. And these are the back of the light particles going away. I'm pretty sure. That's the only way I can interpret that. Those ones right there are the back part, whoops, of the particle that's speeding away. This right here is the back part of this particle that's making this circular pattern. That's what I'm taking away. Alright, I think I'm going to wrap this one up, but this is red and green coming through at the same time. The green is pushing the red right out of the way, making a barrel roll. Never does that in nature. Then the green reconcusses way out here because it's got so much more energy. The green particles are the same as the red, which are the same as the blue, and the blue spins just like all the rest of them, just like this. Here it's so fast that you can't tell it's got two particles. Here it shows up that you can see that there's two, and it's obviously slowing down. And we obviously accelerated it. So all the things they're saying about light, really everything that is wrong in physics right now. That's why I say, pay attention to what I'm showing, and you're going to be way ahead of all the physicists. The physicists are wrong basically about everything because they don't take into account dipole electron flood theory. Once you get past that, and you look at dipole electron flood theory, if you can say I'm wrong, let's discuss it. This is a 5-minute read if you read slow. This is what it looks like. I had another design here that I don't think is right. I think it's the one that where all the black goes to the center, surrounded by all the white. Originally, I thought it was layered. I don't think that's correct. I think it's this one here. Now, and I said this is 1,839 of these little tiny dipoles make up a proton. 1840, which is neutral, make up what they would call a neutron. And here it is, the white and the dark together make the gluon. All right, they're right. A gluon is a Dirac neutrino. And these are the two particles that make it. And the black never gets bigger and never gets smaller. It weighs the same for every green, black, white, red, green, blue, it doesn't matter. The black is one size fits all. The white can go big and go small. And photons are just two of these back to back. And there's some changes in virtually everything. And I'll talk to anybody about this. I will discuss this with any expert that claims to know that I'm wrong. And then we can discuss why I say I'm not wrong. And I have the evidence to show I'm not wrong. And therefore, I have never been approached to claim that I'm wrong other than just being assaulted by people that claim to know what they're talking about. And obviously, I don't know why they couldn't see this at Fermilab. I mean, this is just 100% exactly identical to what they're showing. It's what we found. We used light. We didn't have to start with these big, gigantic particles. And this freaked them out that we could see this using CMOS. Nobody understood this. CERN didn't understand this. Geneva, University of Geneva didn't understand this. Fermilab didn't understand this. Lawrence Livermore didn't understand this. Nobody understood it. CMOS is made to pick up these particles. And now they realize that, and they did upgrade CERN to use CMOS. So I'm going to leave it at that for now. I'll probably, if I see enough comments say, I want you to do more, I'll do more on this. And if not, well, that's probably enough. I've shown, it's pretty obvious what I've shown. Covers all the bases. Dipole electron flood theory wins. Unless they can come up and somebody starts to protest and say, no, Roger, you're wrong. Here's the story. I win. If nobody protests and comes up and talks against me, I win. Silence means you lose. All right, you understanding this at Fermilab and at Lawrence Livermore and CERN and all of them. If you remain silent after I have shown this, I win. That means dipole electron flood theory is the new standard model. All right, I love you all. And it is the new standard model of dipole electron flood theory. It's 100% perfect. It works for every single situation, covers dark matter, covers gravity, covers the speed of light, covers the plasma. I mean, 100%. All right, I love you all. I'm just going to keep blurting this stuff out until it gets understood, because there's so much that filters down from this. It's not just that I'm right and they're wrong, which is kind of true. It's the fact that this changes a lot of the things that we thought. I mean, everything that we thought we need to re-examine. I mean, literally everything. That's all I have to say. I still love you all. Have a sterling afternoon and drive carefully.